To operate a single unmanned aerial vehicle, or UAV, you need enough processing power to map the immediate environment and navigate safely. When you multiply that single vehicle into a coordinated fleet of hundreds, the math breaks down. Routing an individual drone from point A to point B is a computationally solved problem. Scaling that exact same logic to a swarm introduces an exponential explosion in the state action space, where every single vehicle's decision instantly alters the required calculations for every other vehicle. The system must execute two immediate mathematical constraints simultaneously. First, it has to minimize the global path length to conserve fuel. Second, it must calculate real-time collision avoidance for every intersecting trajectory. Layered directly on top of those are two more requirements: maintaining unbroken multi-hop communication topologies so the drones can share data, and doing so while minimizing the decentralized battery drain across the entire fleet. This diagram illustrates these four constraints mapped onto a specific 3D topography. We can see the spatial relationships established between the starting point, the complex terrain features like mountains and buildings, a moving obstacle represented by the helicopter, and the final target point. Calculating exact deterministic flight paths for every single agent in this specific environment forces classical algorithms into a processing bottleneck. Every static obstacle requires a precise mathematical boundary to be rendered and avoided by each UAV. Adding a dynamic obstacle, like the moving helicopter, breaks traditional predictive modeling entirely. The swarm's environment is no longer static. It shifts frame by frame, rendering pre-calculated routes obsolete before the drones even reach them. The sheer volume of simultaneous interactions, drones avoiding buildings, the helicopter, and each other, requires abandoning traditional step-by-step routing frameworks. The onboard computers simply cannot process that many rigid equations fast enough to stay in the air. Swarm robotics requires architectures designed entirely around probability. To keep the swarm flying, the math cannot aim for absolute precision. It must be good enough, and it must be fast enough. This is a chart showing the statistical breakdown of published papers on multi-UAV path planning algorithms. It proves that the industry has fully pivoted away from classical mathematical approaches in order to solve these exact scaling problems. The massive 38% slice represents meta-heuristic algorithms. These are bio-inspired frameworks that mimic the behavior of natural swarms, like bees or birds, to find efficient routes without calculating every exact variable. The 36.7% slice represents hybrid algorithms. This is the fastest-growing sector of research, merging different models to offset their individual weaknesses. Compare those massive sectors to the 2.5% classical slice. At the scale of modern drone swarms, traditional pathfinding math has been practically abandoned. To understand modern hybrid architecture, we have to reverse engineer its evolution. We must trace the failures of classical heuristics, the efficiency of bio-inspired models, and the real-time adaptability of deep reinforcement learning. Each new algorithmic model was invented explicitly to bypass the mathematical failure of the one that came before it. This flowchart details the artificial potential field approach. It defines an attractive field pulling the UAV to its target and a repulsive field pushing it from obstacles. But computing this repulsive function for every obstacle simultaneously overloads the processor, causing drones to crash. This flowchart details the rapidly exploring random trees algorithm. Nodes probabilistically branch out, verifying collision-free pathways step by step. But generating these search trees for dozens of agents causes exponential lag. Memory constraints make it impossible to run online during a live flight. Classical algorithms offer strict mathematical guarantees for finding a path, provided one exists. However, the processing overhead required to find that perfect route disqualifies them from real-time execution. To drop computational overhead, engineers turn to meta-heuristics, bio-inspired swarm intelligence. By mimicking nature, these algorithms bypass the need for exact spatial rendering. This flowchart maps the fruit fly optimization algorithm. Instead of rigid geometry, it tracks a gradient metric called smell best. If met, it uses sine functions to exploit the local area. If not, it deploys a randomized search radius to escape dead ends, drastically reducing system complexity. Metaheuristics save immense amounts of computational power. They trade absolute deterministic precision for gradient approximations that are fast, efficient, and successfully keep the swarm moving. Metaheuristics are highly efficient, but they possess a core weakness. They struggle to adapt to rapidly changing constraints, like high-speed moving obstacles or sudden atmospheric shifts. This diagram shows reinforcement learning. The swarm acts as the agent, pushing an action into the environment. The environment pushes back with a new state and a reward. This continuous loop lets the swarm update its behavioral policy based on real-time feedback. This flowchart details deep reinforcement learning's backend. The system must constantly initialize networks, select actions, parse rewards, and sample data. As the swarm grows, the sheer volume of simultaneous actions causes the algorithm to massively overestimate paths, leading to dangerous navigational errors. Resolving those errors require deeper, larger neural networks. Running these heavy neural networks across a decentralized fleet consumes immense amounts of onboard battery power. Machine learning provides an unparalleled dynamic adaptability, but pure neural network models are far too power-hungry and slow to train to be executed on the fly by a live drone swarm. The modern solution is the hybrid architecture. Engineers embed a highly efficient metaheuristic directly inside the machine learning loop, merging both models. This flowchart maps the Whale-inspired DeepQ network. The primary gate executes actions based on deep learning, but a secondary gate forces the Whale optimization algorithm to dictate action selection, effectively hard-coding a bio-inspired exploration ratio directly into the neural network's blind spots. Hybrid architectures achieve fast convergence, dynamic obstacle avoidance, and real-time execution. They let machine learning handle rapid adaptability, while metaheuristics handle the heavy lifting of spatial exploration. Hybrid algorithms currently dominate performance metrics in simulations, but deploying them into physical airspace exposes a major structural flaw in how the drones actually talk to each other. This diagram illustrates the physical standard for swarm deployment, the leader-follower model. A central controller UAV acts as the routing hub. Routing every path planning request through one controller creates a massive single point of failure and establishes a severe communication latency bottleneck when scaling up. To bypass this, physical hardware networks are shifting toward distributed and decentralized architectures. In a true decentralized state, every single UAV must run its own hybrid algorithm, maintaining peer-to-peer consensus without draining limited battery bandwidth through excessive packet loss. Solving the algorithmic equation was only half the battle. The physical network hardware and communication topology must evolve to support this decentralized processing. Swarm robotics has moved completely away from rigid, deterministic mathematical mapping. The processing cost is simply too high. Operating inside dense, dynamic environments explicitly demands the flexibility of probabilistic heuristics and the rapid adaptability of deep learning. The engineers building the next generation of autonomous swarms must design architectures that know exactly when to explore like a fruit fly and when to exploit a known path like a neural network. The future of flight relies on algorithmic efficiency prevailing over brute force computation. The ultimate multi-UAV architecture doesn't attempt to compute everything, it computes exactly enough.